Okay, welcome back. In this section we're working with trigonometric equations. Very, very important stuff here. You'll be using this again and again as you take calc, hopefully after trig. Okay, so periodic functions cause infinite solutions. The equations we'll be looking at will have an infinite number of solutions. Okay, so for example, let's just take a look here at number 11 in the book, and if you're following along, it's on page 703. Find all solutions, and all solutions, not just one solution, but find all solutions to the equation sine of x equals root 3 over 2. Okay, on the unit circle from 0 to 2 pi, we know of two solutions, right? The first one, the most obvious, is the reference angle solution that we have memorized, pi over 3. Okay, so we know x is equal to pi over 3. That's one solution. Another solution is where sine is also positive, that second quadrant, so this angle. So x also equals 2 pi over 3. Would be another solution. Okay, and then the other solutions, so there's an infinite number of them. How do I get those? Well, you just kind of add multiples of 2 pi onto these two primal solutions. Okay, so prime, kind of like the origin solutions, the main solutions from which you can get all other solutions. Okay, the base kind of solutions. The basis, right? Okay, so how are we going to write that out, right? So anyways, if you're doing with pi over 3, what I'm saying is then you can add in or subtract 2 pi over 3 and get more solutions. So if you add 2 pi to pi over 3, you're going to go full circle and then end up back where you started, okay? But you can also subtract, right? So you can also go in the other direction, subtract 2 pi, and you go full circle and end up right back where you started. So you can subtract. You can also add multiples of 2 pi, right? So you can add in 4 pi, right? 2 times 2 pi. So you'd go around once, and then you would just go around again. You end up where you. So you can add in basically any integer multiple of 2 pi and still have another solution. So the question really then is, how do I write that in math terms? I could show you the little picture of what I mean and all that jazz, but how am I going to write that out? Okay, so what am I saying? I'm saying I can always add in 2 pi and get kind of new solutions, kind of, but multiples of 2 pi, right? So hey, instead of writing 2 pi, let's write 2 pi n, and that n indicates where we can multiply 2 pi by pretty much anything. Right? We can't use fractions though, so we have to indicate that n is an integer value. So n is in the set of integers, which just means like -1, -2, -3, on and on, and also 0, and also 1, 2, 3, 4. So you can plug any of those numbers. So maybe I should write that, dot, 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 -3, -2, -1, 0, 1, 2. These are all integers, and on, in both directions, on and on. It's usually what you would plot on the number line, those numbers. Okay. So I could substitute any of those numbers in for n, and that would also be a solution. So you could do that with pi over 3, but you could also do that with 2 pi over 3, right? So if you added in another 2 pi, you would get back to where you started. You could add in 2 times 2 pi, so I go around once and then twice and then get back here to where I started. You can also subtract. So again, we're going to add in 2 pi n. Let me put that in white. So plus 2 pi n, and then these would represent all your solutions. Right? So it would be these two things that would represent all your answers. Okay, so let's look at a couple more of those. Right? Let's just go through and kind of see if we can get a whole bunch of these. So 12, we have cosine of x equals radical 3 over 2. Okay. So again, the way you approach this is you kind of look for the reference angle answers. first. The answers that are in between 0 and 2 pi. So of course you get your reference angle, just pi over 6. But then there's another solution, right? And that's where cosine is also positive. That's 11 pi over 6. So you put that as your other solution. And then just add in multiples of 2 pi n, or multiples of 2 pi, which is 2 pi n. Okay, so that would be those would be your solutions. So x equals pi over 6 plus 2 pi n, or, and maybe we should put an or in there, or from the other one. So or in here. Let's try another one. So 13 tan of x equals 1. Okay. Okay. So the angles, that would give us 1. So there's 1 here at pi over 4. So we could say x is pi over 4 plus, eventually plus 2 pi n. But there's another one, right? So tan is also positive, and the third quadrant, where sine and cosine are both negative. Okay, so what angle is that? 1 pi, 2 pi, 3 pi, 4 pi, 5 pi over 4. Okay, this is the answer. It's just like what we were doing before. It's this or this. But unfortunately, the math people, they always want the ultimate, most simplified answer, right? So there's an even easier way to write this because of the way that these two angles are kind of just pi apart, whereas these other angles, if you look at them, the distance between the two angles, so over here, let me redraw those. We have pi over 3 and 2 pi over 3. It's not some sort of nice angle like pi over 2 or just pi. And same deal here. The distance between these two is really it's 2 pi over 6, which is pi over 3. The distance between these angles is pi over 3. So it turns out if you have this nice kind of uniform distance between the two angles, and there looks to be a kind of like symmetry going on, you could simplify it into one thing. Okay? You could just say x equals pi over 4 plus multiples of pi. So you say pi n. And you see it works, because if you just add in 1 pi to pi over 4, you're going to get that 5 pi over 4. Okay? If you added in 2 pi, you'll be back to where you started. Okay? And then if you add in 3 pi, you're going to get one of these pi over 4s. So this thing here, this ultimate answer, will kind of kill all the birds with one stone. Honestly, on a written test, I'd take this answer too. I ain't got no problem with this. It's just a bit redundant. Okay, you have to write out a little bit more, and it's kind of easier to remember with regards to you as a student having to memorize all these processes, right? Okay, so let's look at another one. I don't know. Let's try 15. So here we have cosine of x equals negative 1/2. Okay. Okay, so you just kind of begin in the angle in between 0 and 2 pi and look for your solutions. So we're talking pi over 3s is the reference angle, but we want cosine to be negative. So 2 pi over 3 is one solution. And then another solution down here where cosine is also negative would be 4 pi over 3. So x equals 4 pi over 3. And there's no real nice kind of distance, so you can't like travel, I'm going to go, sure, you can travel, you can add in just 2 pi over 3 to get 4 pi over 3. But then if you try to add in another 2 pi over 3, you're not going to have a good day, right? It's not going to put you back on to 2 pi over 3 like you did with the tan version. Okay, so what I'm saying is there's just no way to nicely simplify this thing into one expression like we did above. You really have to just keep it as two different things and add in the 2 pi n's. Okay, so it's one or the other. Let's look at number 17, where we have tan of x equals 0. And this is another one that you're going to see you can simplify into one expression. Tan will be 0 wherever cosine's equal to 0. So that's going to be at x equals pi over 2, and then x equals 3 pi over 2. Okay, so this time, yeah, you can just add in pi over 2 and get to 3 pi over 2. Oh, sorry, not pi over 2, but just pi, right? And then you can add in another pi, and you kind of get back to the pi over 2 set, right? So I mean, originally you're thinking, all right, I have to add in 2 pi n. That's kind of the standard deal, and this would be a fine answer, okay? That would be fine on my test. But what I'm saying is the math people aren't going to like that answer, okay? And probably my math lab won't like it either. You have to simplify it into x equals pi over 2, and you just take the first one, okay? You don't mess with the second one. Pi over 2 plus pi n. I mean, you could write 3 pi over 2 plus pi n. That would be equivalent, okay? But just for the sake of sanity, we kind of want everybody to have the same language. And it's the pi over 2 plus pi n is what's going to get the job done. Let's look at maybe, I think we're sort of beating this to death. Let's look at some of these multiple angle problems, okay, and then we'll kind of move on to a different spiel. Here's 25, and we have the sine of 2x equals radical 3 over 2. Okay, same spiel. The big difference here between this one and the first one is the angle inside the function. Like you have sine x of radical 3 over 2. This is sine of 2x all equals radical 3 over 2. It's pretty much the same game. All right, so you're going to identify the particular solutions in between 0 and 2 pi. So for root 3 over 2, it's pi over 3 is one of the solutions, and then 2 pi over 3 is the other. Okay. So instead of writing x equals, you're going to borrow this, and you're going to write 2x equals, okay, one solution was pi over 3, or 2x equals, the other solution is 2 pi over 3. Okay. And then you're just adding in multiples of 2 pi for the rest of your solutions. Okay, that's the same as before. Now the different part is the last part. You have to divide both sides by 2, okay, or multiply both sides by 1/2 to get your x equals answer. Okay, so you multiply there by 1/2, here by 1/2. You'll end up with x equaling pi over 6, okay, when I distribute this, and then plus pi n. So 2 pi n over 2 is just pi n. And then you do the same thing to the second equation. So you multiply both sides by 1/2, and you get x equals 2 pi over 6 plus pi n. Okay. Of course, 2 pi over 6 is just pi over 3, so maybe we should just write pi over 3. Okay. Should we do one more? Let's do one more, and then we'll move on. Okay. So let's try 33, and we have sine of 2 theta over 3 equals -1. Okay, there's only one angle in between 0 and 2 pi that gives me -1, and it's this angle here at 3 pi over 2. So I'm going to say, okay, I borrow this angle, 2 theta over 3 must equal 3 pi over 2 for it to equal -1. And then on top of it, you're just adding in multiples of 2 pi. Okay, so for theta equals, for that answer, what you're going to do is multiply both sides by 3/2. Okay, so this side by 3/2. Distributing, you'll get 9 pi over 4 plus 3 pi n, because the 2's will cancel on the second part. Okay. Okay. Right. So these trig problems aren't that hard. These I could barely call them equations, right? So let's look at something that's a little more complicated, and I'll call this section 2 in my notes. I have a title for it. It's just what equations involving single trig functions. It's the same title they have in the book. I'm just trying to abbreviate so we don't have to sit here writing for an hour. single trig functions in your equations. What you want to do here is isolate the function. Just like you would isolate the variable, here you're isolating the function. So before, you would have something like 5x plus 1 equals 3x, and you would solve. Now, though, instead of having x, you have like a trig function, 5 sine x plus 1 equals 3 sine x. Okay, so let's take a look at problem like number 22, and let's see, make sure that the direction is going for us. Number 22, we want to find all solutions. Okay, and the equation 5 sine of theta, basically just the kind of problem I gave you in my little mini now example. So anyways, 5 sine theta plus 1 equals 3 sine theta. I used a x instead of a theta. And the now. Okay, hopefully that's clear. Okay, anyways, you have to isolate the function. So you're going to collect all the signs on one side. So I'm going to move the 3 sine theta over to the left. So subtract 3 sine theta from both sides, and then subtract 1 from both sides. Okay, so you end up with 2 sine theta plus 1 is 0, and then of course you get 2 sine theta equals negative 1, and then you get sine of theta equals negative 1/2. Okay. And at that point, you basically have a problem just like the ones above. Okay, so you solve it using those methods. We're looking for infinite solutions in this case. Okay, so sine of theta, the reference angle to equal 1/2 is the pi over 6, right? But we want where sine is negative, and that'll be in the third and fourth quadrant. Okay, so that'll be where theta equals, so here is 6 pi over 6, and then that's 7 pi over 6 for one of them, plus 2 pi n. So you're just always kind of tacking on the plus 2 pi n. Or the other case where theta equals 11 pi over 6 plus 2 pi n. And there's no real way to simplify that into just one thing, so we're going to leave it as is. Okay. The next kind of problems that I do, we're gonna just solve them on the interval from 0 to 2 pi. Okay, and that's kind of how a lot of questions will go in general. You won't have to give us the infinite solutions, but I hope you can give me the infinite solutions if you need to, because in calculus, it seems like you often need to kind of write up infinite solution answers. Okay, and a lot of my students, for some reason, aren't figuring it out. Okay, so hopefully you can master this infinite solution case, but it's pretty easy. It's always you get usually 2 answers, and you just tack on a 2 pi n, and then if you can, like with the pi's, the tangent functions, usually you can kind of simplify those if there's this nice symmetry going on. But even if you couldn't, you could still just write this answer, but it's redundant, right? Okay, so anyways, let's move on then. Just basically solving on the interval from 0 to 2 pi. Okay. I mean, even when I solve it this way, I usually write out my solutions as infinite solutions, but then I turn around and kind of just give you the solutions in that interval. So anyways, without further ado, 25, the sine of 2x equals root 3 over 2. Right? Did I already do this? It seems like I kind of did it, but I did the infinite version. Yeah. Okay. So this time we just want the answers in between 0 and 2 pi. So, right, in between 0 and 2 pi, what are the 2 angles that give me root 3 over 2? And of course, I'm going to borrow the 2x and make my equations that way. Okay, so 2x would equal what? Pi over 3 is one of them. Or 2x must equal, so 1 pi over 3, and then looks like 2 pi over 3 would work, right? 2 pi over 3. And because you have this multiply angle, you just really can't say, well, it's only pi over 3 and 2 pi over 3 as your solutions. because when you divide by 2, you may get more answers, believe it or not. So let's go ahead and write up the infinite solution kind of answer. Okay. And then we're going to divide everything by 2. So I get x equals pi over 6 plus pi n. On the other one, I get x equals pi over 3 plus pi n. Okay. And then I'm just going to produce those answers. So the first one is pi over 6 plus 0. Okay, so x1, I guess. Another solution would be pi over 6 plus pi. So 1 times, so this is when n is 0. The first one is plus pi times 0, right? So that would just be pi over 6. Now I'm going pi times 1. So that's pi over 6 plus 6 pi over 6, which is 7 pi over 6, which is still in between 0 and 2 pi. Right? X sub 3 is pi over 6 plus 2 pi. That's going to be bigger than 2 pi, right? If you add something to 2 pi, it'll be bigger than 2 pi. So we stop. Okay, let's try the other one. So x3, starting with pi over 3, and then adding in pi times 0. That will just be pi over 3, of course. And then you go x4 is pi over 3 plus pi times 1. So 3 pi over 3 plus pi over 3 is 4 pi over 3. So we get 4 answers. X is equal to pi over 6, 7 pi over 6, pi over 3, and 4 pi over 3. Okay. Let's just make sure I'm right. Yeah, okay. Let's look at another one. So this is 31 from the book. So I have tan of x over 2 equals root 3. Okay. So again, I go to my unit circle. I'm looking for angles that give me root 3. So that looks like pi over 3, I believe, is one of them. And then you're going to get another one in this third quadrant. So x over 2 equals pi over 3. And I could tell because these angles are perfectly apart, and I could kind of travel from one to the other by just adding constant multiple of pi. And I could just write pi over 3 plus pi n. The other way, of course, will still work. You know, you get 2 pi n, and then x over 2 equals, it's actually 4 pi over 3 plus 2 pi n. You know, you could do it this way, but you could simplify both of these into x over 2 equals pi over 3 plus just pi n. Okay, so let me work with the simplified. I mean, that's kind of the way we should do it. So let me work with this thing. Okay, so I got x over 2 equals pi over 3 plus pi n. I'm going to multiply everything by 2, so I get x equals something. So I get x equals 2 pi over 3 plus pi n. And then I need to find all solutions in between 0 and 2 pi. So my first solution is multiply 0 times pi. So I just get 2 pi plus 0 pi, which is 2 pi over 3 plus 0 pi, which is 2 pi over 3 plus 0, which is 2 pi over 3. Another solution, whoops, did I multiply this by 2? I did. Whoops, and I screwed up another one. So originally it was this, and then when you multiply both sides, you get 2 pi over 3 plus 2 pi n. I messed that up, I'm sorry. Then there is no x2, right? So because you would have 2 pi over 3 plus 2 pi times 1, right? And that would be bigger than 2 pi, so we would throw that out. So there's just one solution. Okay. The next kind of problem, we're going to take this one up a notch. This kind of solving trig functions. So they're going to become quadratic. So the quadratic form, I may have screwed up my Roman numerals. I apologize if that's the case. Yeah, this is section 3. Get rid of that. Okay, so these are quadratic forms, and the spiel is kind of just like what I was doing with the where you have one trig function. So before you would have had something like x squared plus 2x plus 1 equals 0, and you'd have to solve that. And now instead of x, you're going to have like sine in there. So sine squared plus 2 sine x plus 1 equals 0. And the solution will work the same way. So before you'd have x plus 1. Unfortunately, I have x plus 1 times x plus 1. Not a very interesting example. Here I have sine x plus 1 times sine x plus 1. And then when you set the parts, the solution here would be x plus 1 equals 0. So x is negative 1. The solution now is going to look like sine of x plus 1 is 0. So sine of x is negative 1. In other words, now you end up with one of these kind of problems, right? So you're just looking for all the solutions. And again, we're going to work just in between 0 and 2 pi. So in this case here, you would have, where is sine negative 1? Well, that's this angle down here. So x equals 3 pi over 2 would be the only solution. Okay, so let's look at some of the ones from the book. And again, we're just restricting our solutions to the interval from 0 to 2 pi. Okie dokie. So number 43. I think that's the first one. Yeah. Okay, so we have 2 sine squared x equals sine of x plus 3. Okay. So first things first, get it set equal to 0. So the original examples here, they were already set equal to 0. So that's kind of we have to do that first. So sine squared x, then you have subtract sine x on both sides, subtract 3 on both sides. You get that. Then you're going to factor it. Okay, so it's going to be 2 sine x and then sine x. Okay, this is going to be plus and minus. I don't know which one. It has to be 3 and 1 or 1 and 3. It has to be 3 and 1, otherwise the middle term, the inner and outers, would add to something weird. And then the bigger number has to be negative, and this has to be positive. Okay? And you can FOIL it back out and see it works. 2 sine squared outer, 2 sine x minus inner, minus 3 sine x, and then minus 3. So it works. Okay, from this point, you end up with 2 equations for the price of 1, right? So you get 2 sine x minus 3 is 0, and you also get sine x plus 1 is 0. And then we got to solve these. Okay, so the first one, we have 2 sine x equals 3, and then you get sine of x equals 3 halves. You remember that's an issue because sine, the sine of x function is wedged in between 1 and negative 1. It's because of the amplitude. So sine of x can never equal 3 halves. So here there's no solutions. Okay, let's look at the other guy. Sine x equals negative 1. Okay, so where does that happen? That happens at 3 pi over 2, when x is 3 pi over 2. And then every 2 pi afterwards. But if you add 2 pi to this, you would go out of the range from 0 to 2 pi. You go out of this range. So we won't include any other answers. And your only answer is 3 pi over 2. So there's other things that are kind of quadratic but not quite, like number 59. You have sine of x plus 2 sine x cosine x equals 0. Here you can factor it. So it's kind of like x plus, I don't know. It's almost like x. Well, factor it. Okay, factor a common sine x out of it, and then it looks like like the end step in a quadratic. You just set each part equal to 0. Okay, so this would be 1 plus 2 cosine x equals 0. And then you set each part equal to 0. Sine x is 0. And then 1 plus 2 cosine x is equal to 0. Okay? And then you solve those in the appropriate range. So where is sine of x equal to 0? That happens at 0. And that happens at pi, and then at 2 pi, but we don't include 2 pi, right? So you see that open parentheses on 2 pi, we don't include it. Okay, so just x equals 0, and then x equals pi. Okay, how about this other guy? So we have 2 cosine x equals -1, so cosine x equals -1/2. Okay, so the reference angle for cosine x equal 1/2 would be pi over 3. Cosine is negative, and the second and third quadrants, so we have 2 pi over 3, and then 4 pi over 3. Okay. And those are our only solutions. X equals 2 pi over 3, and then 4 pi over 3. Okay, because you couldn't add 2 pi to either of those because you would go out of the range from 0 to 2 pi. Okay, so those are your answers. And you can circle them on the test. That'll be good enough for me. Okay. Sometimes you kind of get stuck, and you could use identities to get around it. You don't want to get too carried away with the identities. You don't want to use the obscure identities that I don't have you memorized. I haven't had you memorize them, but you can still kind of, if you get in a jam, you can use them to an extent. Okay, so using identities. Okay. So what I would recommend you do is to get everything in terms of one trig function. Everything into terms of one trig function. And get everything to have the same angle. So you don't want to have like the sine of 2x and then on the other side sine of 5x. That's going to be a pain. You want everything in terms of sine of 2x if possible. So get everything in terms of the same angle. Okay, so let's look at some examples of that. And we'll start out with 63. Again, we're sort of restricted to the range from 0 to 2 pi. So here we go. 2 cosine squared x plus sine x minus 1 equals 0. So this looks like a quadratic, but it's not quite, because we have one cosine and one sine, or actually 2 factors of cosine, and then one sine term. Okay. So the trick is to get everything in terms of sine. Okay, and you can do that using our Pythagorean identities. Cosine squared, we recall, is 1 minus sine squared. And then you can actually make it into a quadratic, right? So this is 2 minus 2 sine squared x plus sine x minus 1 is 0. And then you can, let's move everything to the other side and flip-flop the equation. So you get 2 sine squared x minus sine x minus 1 is 0. Then we can factor it. So you get 2 sine x and then sine x. And then we have 1 and 1. And it looks like we have to put a minus on that and a plus on that. Okay. Set each part equal to 0. Over here. And then look for your solutions. So for negative 1/2, the reference angle for 1/2 is pi over 6. Sine is negative in the third and fourth quadrant. So we're looking at x equaling 7 pi over 6 and then 11 pi over 6. And that would be as good as you get. If you add any more multiples of 2 pi, it's going to go out of the range from 0 to 2 pi. And then sine of x equals 1, so that's when x is pi over 2. That'll only happen there in that interval. Okay? So those will be our solutions. Good. Let's look at another one. So we have sine of 2x equaled cosine of x. So when I was first talking, I said get everything in terms of one trig function and get everything in terms of the same angle. Sometimes you can do one, but you can't do the other, and vice versa. Okay. So in the first problem, the issue wasn't that the angles were different, right? So both of them just have an x. There's not like a 2x and then a 5x, right? So what I did was get everything in terms of sine, and then we could solve it. Okay. This time, it's not going to be, the case where we can get everything in terms of sine or cosines. We just want to get the same angle on both sides. Okay, so what I'm going to do is rewrite sine 2x using our 2 sine x cosine x formula, and that will equal cosine x. And then you can move the cosine x over, and it will be one of these factoring problems. It'll be just like number 59. Okay. So as you go through the questions, you're collecting experiences, and hopefully you remember those experiences when you go to solve further problems. Right? We factor out cosine x. We get 2 sine x minus 1, 0, so cosine x is 0, and then 2 sine x minus 1 is 0. In the unit circle, we're thinking of x equals pi over 2, and then and then 3 pi over 2. And you can't add pi. 2 pi to either one of those, or you'll go out of the range. And then this guy, 2 sine x is 1. So sine x is 1/2. And then the reference angle for 1/2 is pi over 6. Sine is positive in the first and second quadrant, so we'll have x equals pi over 6 and then 5 pi over 6. And that would be it. So that'd be those 4 solutions. Okay. Let's try another one. This is 73. So I have cosine of 2x plus 5 cosine of x plus 3 equals 0. Okay. You can look through the identities and look for something that would be useful. You could turn this one into a quadratic if you do an identity on cosine 2x. So the identity for cosine 2x would be one of them is 2 cosine squared theta minus 1. Okay, and then plus 5 cosine x plus 3. So if we replace this cosine 2x with a cosine squared, we could turn it, basically we've turned it into a quadratic type. Okay. So note everything's in the same function, everything's in terms of cosine, sort of, and then the angles are the same. Well, they should be the same. I forgot to put x instead of theta. Sorry about that. Okay, so now it's quadratic, and we should be able to solve it. So I have 2 cosine squares, x plus 5 cosine x plus 2. Okay, and then we could go ahead and factor it. And we get 2 cosine x, probably plus, and then 2 and 1. First off, I could already tell this 1 isn't going to have any solutions, right? Cosine x will never be negative 2 because cosine x is always bounded in between 1 and negative 1. Okay? So no help there. Then the other guy, 2 cosine x plus 1 is equal to 0. Okay. 2 cosine x equal to negative 1. So cosine x is equal to negative 1/2. And then the reference angle for 1/2 is pi over 3. We want, where is cosine negative? So it'd be down here and up here. So that's where x is 2 pi over 3 and then 4 pi over 3. Those will be the only solutions then. Okay. Okay. Let's move on to using your calculator to solve. Well, let's do one more of these, and I want to change the angle because in these ones I didn't really have to worry about the infinite solutions, right? But if you change the angle, that becomes an issue. So I'm gonna borrow this thing, okay, and kind of work with it just to show you what happens if the angle is different. Okay, so hopefully 3 years later, I'll be able to move down the page. Okay, so I'm going to change this a little, and you'll see in the interval from 0 to 2 pi, you have to be careful. Okay, so this would have been equal to 0. Let's just change it a little. So sine squared of 2x minus sine of 2x minus 1 equals 0. You can, it's quadratic, even though I put a 2x in there, it's still a quadratic form. So you have 2 sine of 2x and then sine of 2x, and then this will be minus, no, this is the plus, and then this one's minus, and this is 1. Okay, so I'll have 2 sine of 2x plus 1 is 0. Seems like I'm doing something wrong. Where did I take that guy from? No, I'm fine. And then also sine of 2x minus 1 equals 0. Okay. So the first guy, let's solve this one first. I get 2 sine of 2x equals negative 1. And then I get sine of 2x equals negative 1/2. Okay. So this is where you got to be a little careful, because you put, instead of putting x equals, you know, for negative 1/2, again, the reference angle is pi over 6, so sine is negative in this quadrant and this quadrant. Instead of putting 7 pi over 6 and 11 pi over 6, x equaling those answers, you have 2x equaling those things. So you have 2x equaling the 7 pi over 6, and then you have 2x equaling the 11 pi over 6. And this becomes an issue because now it's a smaller angle, and you're going to be able to fit more answers in the range from 0 to 2 pi. Okay, so you kind of have to include the 2 pi n in your answers when you have these multiple angle problems, when you have 2x instead of x, or if you have 5x instead of x, or you have 12x instead of x. You're going to have to pull this stunt. So anyways, this will be x equals 7 pi over 12, because you're multiplying both sides by 1/2. 7 pi over 12 plus just pi n, and then this one is x equals 11 pi over 12 plus pi n. Okay. So your first solution, x1, is 7 pi over 12 plus 0 pi's. Then your second solution will be 7 pi over 12 plus 1 pi, which is the same as 12 pi over 12, which is equal to 19 pi over 12. And then your third potential solution would be 7 pi over 12 plus 2 pi. And then 2 pi is 24 pi over 12, but that's going to be out of the range, right? That'll be bigger than 2 pi. That'll be 31 pi over 12. 24 pi over 12 is 2 pi. So no, this one won't work. Okay? But you do get 2 answers instead of just that one. And then from the other set, so maybe I shouldn't have wrote x1 because I'm listing a bunch of answers. So for the other set, you start with 11 pi over 12, right? And then you have 11 pi over 12 plus a pi, which is really 12 pi over 12, which is equal then to 23 pi over 12. And then you have the next one, which is 11 pi over 12 plus 2 pi, right? And of course, that one will go out of bounds again. So just from this one part, we have 4 solutions. We have x equals 7 pi over 12, 19 pi over 12, 11 pi over 12, and then 23 pi over 12. Okay, let's look at our other guy. So sine of 2x minus 1 is 0, right? So we have sine of 2x minus 1 is 0. So we'll have sine of 2x equals 1. And again, we're kind of thinking the reference angle. So sine of pi over 2 is 1. So we got 2x equals pi over 2. And again, I got to be careful. I got to add in the 2 pi n, right? Then if you multiply both sides by 1/2, you'll get x equals pi over 4 plus pi n. And then you're looking for solutions in this interval. So the first solution would be pi over 4. then pi over 4 plus 4 pi over 4. In other words, pi over 4 plus pi. Like pi over 4 plus pi is pi over 4 plus 4 pi over 4, which is 5 pi over 4. And then pi over 4 plus 2 pi, which would be too big. So our final two solutions, pi over 4 and then 5 pi over 4. Okay. So when you have those angles, different angles inside of your sine functions or cosine functions, other than x, you can't kind of do what I was doing. You can't just say, oh, I'll just give you the two angles in between 0 and 2 pi. You're not going to be able to do that because if you have like a multiple of x, like 2 times x, it means it's a smaller angle and you could fit more angles in between 0 and 2 pi. Okay, so the end result is you have to divide by 2, and then you're only adding on pi times n each time, so you can fit more angles in there. Okay, the last topic in here is on calculators, using your calculator to answer these questions. This is section 5. Obviously on a test, I will tell you whether or not I want you to use a calculator to solve. So let's look at example 11. Solve correct to 4 decimals. And we're working on the interval from 0 to 2 pi, as usual. Okay, the question tan x equals 12.8044. So how do I solve that? Well, take tan inverse on both sides. On the right, the tan and the tan inverse kind of cancel each other. And you'll get x equals tan inverse of 12.8044. And this is where you use your calculator. Okay. The problem with this is your calculator answer will not give you all the solutions you want in between 0 and 2 pi. The calculator answer is just going to be one answer, right? And on top of that, that answer may not even be in this interval from 0 to 2 pi, because if you remember the range for tan inverse, it actually goes from negative pi over 2 to pi over 2. Okay. So when you do your tan inverse, you might end up with something that's negative, right? Anyways, let's take a look at this one. Right? Okay, so I plugged tan inverse into my calculator, tan inverse of 12.8. Make sure you're in radians, okay? And you get sort of a calculator answer of 1.4929 radians. Okay. 1.4929 is a little less than pi over 2. Pi over 2 is like 3 divided by 2, which is like 1.5. Okay, you think that way. Okay, so we got one answer. They got the answer in the first quadrant. We need the answer that's also then in the third quadrant, right? So there's a couple ways you can do it. The angle you're getting here is the reference angle, right? So all you need to do is kind of take. So this would be like x1. X2 answer would be the x1 answer plus negative. So it would be x1 minus. Oh, sorry, no. My brain is starting to fall apart. So it's this angle I'm after. Okay, so it's pi plus x1. Okay, so you'll rotate around pi and then add in this angle, and it should give you the second angle that you're after. So this is approximately 4.6344. Okay. Okay, let's look at a different one. So let's try another example a bit like this one. So let's say x is equal to, or tan of x is equal to negative 3.2. Okay, and we go into our calculator, get tan inverse of negative 3.2, and see what that is. Okay, so get my calculator out. It's negative. It's not very happy about this. Negative 72 point. I think I'm in degrees. Yeah, I am. I need to get the radians. Sorry. I was going to say that's ridiculous. Something is wrong. Negative 1.2679. Okay. Okay. We want our answers to be in between 0 and 2 pi, and that answer is not even there, right? So this answer, as it sits, is, inverse tan is from negative pi over 2 to the pi over 2. So it's down here somewhere. Okay. So what you can do is kind of find the reference angle to work with, and then go after the angles for tangent that are in the second quadrant and the fourth quadrant using the reference angle. So to get the reference angle, what you have to do is add 2 pi to this answer. So you're going to go x plus 2 pi and see what that is, right? And that won't even give you the reference angle, right? That's just going to give you an angle. So to get the reference angle, you have to take 2 pi and geez, this is more complicated than I thought, huh? Well, you can just make it positive. You can just flip it over the x-axis, and it'll work. In this case, you may not believe me, but it will. So the reference angle is just 1.2679. So if your angle down here was like negative pi over 3, the reference angle would be pi over 3. If the angle down here was negative negative pi over 6, the reference angle will be positive pi over 6. Okay, so you get the reference angle, and then you want this angle and, or rather you want this angle going around to here, and then you also want this angle going around to here. Okay, so to get the first angle, x1, you're taking 180 and pi and subtracting away the reference angle. To get the second answer, you have to take 2 pi and subtract away the reference angle. Okay, so the first answer, I take pi and subtract away this. Whoops. I take pi and I'm subtracting away 1.2679. And I'm getting 1.877369. And then 2 pi minus that. 1.2679 is 5.0153. Okay. And then you could always check that with your calculator, which is what I'm going to do here. I'm going to pause it and I'm going to check it. Okay, so how did I check it? What I did was just go back to this original equation and plug them in. So tan of 1.87369, and make sure that that's about negative 3.2, which it is. It's like negative 3.19999. And then I try tan of 5.0153 and make sure that's about negative 3.2, which it is. Okay, they're both approximately equal to those. Okay, one more, I promise, and then we're done. A lot of little technical details I got to iron out for you in this section. So plus 3 is 0. Okay, so this one looks quadratic. So it looks like I can go like 2 and 2, right? 6 and yeah. So 2 tan x, and then 2 tan x, and then 3 on one of them, And I want that one. They both have to be negative, right? And then 1. Okay, and then you solve each of those. So 2 tan minus 1 equals 0. 2 tan x equals 1. So you're looking for where tan of x equals 1/2. Of course, we don't know that, so we have to use our calculator. Okay, so we'll have 2 answers. Hopefully, yeah, they'll both be in you know. Okay, so, and then the other one, 2 tan x minus 3 equals 0. So 2 tan x equals 3. So tan x equals 3/2. So x1 is an x2. So I'll go to my calculator to get these. Again, make sure you're in radians. Okay. So tan inverse of 1/2 is 0.4636. That's in the first quadrant, so that we can use that as a reference angle. So that'll be in here somewhere. Then to get the other one, we need the one in the fourth quadrant. So I need to go pi plus x1. So plus pi, and that will be 3.6052. Okay, and then on the other guy, so tan inverse of 3/2 is 0.9828. And again, we don't have to worry about like and this weird one here, this weird example. We don't have to worry about that issue. This one's in the first quadrant, and so the reference angle will just be pi plus that. So 4.1244. Okay. So hopefully most of the problems in WebAssign, not WebAssign, but MyMathLab are not like this example. But that kind of example, I've seen it come up in calculus problems before, so I just have to cover all my bases and make sure you've at least seen it once. Right? Okay, that'll do it for us. Let's call it a day, and I'll see you next time.